Last time, we derived the dielectric constant of ordinary metals by a purely quantum mechanical method, which is the random phase approximation, meaning we sum over all possible contributions to the kind of external potential U, includes the contributions from the other Coulomb potentials V between two electrons. So, compute this U effective, which is influenced by the other Coulomb potential V. But as we pointed out already, so these Coulomb potentials U and V are mutually influenced. So we could equally well to compute the V effective, contribute from the presence of U. Okay, but here we just start from calculating U effective contributed from V, and by summing over all the RPA bubbles or ring diagrams where this bubble represents the kind of like electron-electron Coulomb interactions, and through this the potential V. And when we sum over all our contributions, this is just a geometric series, and it's easily obtain the result, which is this U, the bare Coulomb potential U as function of momentum transfer Q divided by the dielectric constant epsilon of Q. And the epsilon of Q is actually a dielectric constant of function of metals, which is defined as 1 minus V of Q times this called charge susceptibility chi of 0 as function of Q, and chi of 0 is defined as sum over momentum P and spin sigma of this ratio, where in the denominator we have this epsilon P plus Q minus epsilon P, and the numerator we get difference between the Fermi function of MP plus Q and MP. So we can Taylor expand this difference in Fermi distribution function, which is given by this integral, and you cancel this numerator and denominator, and you know that this Fermi function, when t equals 0, is actually the minus Dirac delta function. So partial Fermi function, partial epsilon, is actually minus Dirac delta function at this Fermi energy. And then this is very easy to compute. You get minus density of states of electrons at the Fermi level. So that's what this chi0 of Q is when Q is actually very, very small. So of course this Taylor expansion is valid when Q is very small. But in general, this epsilon is a function of Q and also temperature. Okay, so when Q is not so small, and of course this chi0 of Q is not identical to the just a constant density of states, but it is a complicated function of Q and temperature T. Okay, but here we will simplify this by considering the zero temperature limit and small momentum transfer limit, because we know that in this limit we have this plasma oscillation phenomena, and this plasma oscillation phenomena played a crucial role for this Coulomb screening effect. So let's just determine this density of states of electrons at any energies. And from introduction solid state 1, you know that this is given by electron density per unit volume, taking the derivative of that with respect to the energy. Okay, so the n, the epsilon, is just the density of states of electrons. And from this free electron model in 3D, we know that there's a Fermi spheres, and there's a Fermi volume with a radius of Fermi momentum kf, and so on and so forth. And you could easily get this estimation down, very easily in the free electron model. So you get this kind of a square root epsilon dependence of the density of states for free electron gas. Remember, the unperturbed state is exactly the free electron gas model. So we consider a small kind of perturbations due to this Coulomb energy, and then we start to do RPA kind of expansion. Okay, so, and this is a simple relation between the, say, Fermi volume and electron density, number density. Okay, and the volume of the Fermi sphere is nothing but 1 over electron density per unit volume, and you could get this A0 KF product, which is given by this prefactor times 1 over RS, and therefore RS is given by this combinations. So now we could just plug in all these conventions in solid state, which is this A0 Bohr radius and this electronization energy minus 13.6 electron volt, and also 1 Rydberg constant, which is E squared over 2A0, which is plus 13.6 electron volts. So we could actually, estimate this density of states by plugging this estimation and or this constants. So now we could, use this notation chi0 of q to rewrite this U effective in terms of Thomas Fermi-like wave number ks squared in the denominator of this q square. Remember, so if we get this form and we could Fourier transform this U effective to real space, and this will be Yukawa type of potential, which serve as a cutoff in real space, and this Ks is actually this QC. And this is the homework. We can show that this Ks in this small momentum transfer limit and zero temperature limit is given by this Thomas Fermi wave number, which is minus 4 pi e squared chi0 of q, which is given by this density states at the Fermi level times 4 pi e squared. And if you use this, units defined here to re-express the density states, this is given by 4kf divided by pi times A0, which is about 4.6 divided by Rs. So you could actually derive this estimation. And this Ks here is nothing but a Thomas Fermi screening wave number, KTF, that we derived earlier. And just to give you some idea of how this numbers in the realistic metals, Ks is about 0.1 divided by nanometer. So For example, this Ks is about 2 times 10 to the 8 divided by centimeter, which means that you have the screening length is about that much in real space, meaning your 1 over r potential is going to be cut off when r is actually larger than this Ls. And this is another homework. You can also compare this estimation of a Ks squared right here to the previous derived Thomas Fermi wave number KTF squared, which is given by 6 pi NE squared divided by Fermi energy. And you could check whether they are really the same. I think that's probably the full story of this pure quantum mechanical treatment of a screening of a Coulomb interaction. And you could do the same thing like we did here for U effective, but now you could actually compute V effective, which is the effective Coulomb potential between any 2 electrons. But remember, this time there's external electron density perturbations nearby, which is U. So now the presence of a U, which is different source of this Coulomb potential due to this small density variations, is going to modify the bare Coulomb interactions in almost exactly the same way that we computed here for this U effective. Namely, the VV effective is going to be having exactly the same form as U effective. So the only difference here is that for V effective, this is this numerator, we have this electron charge E squared, but in the U effective, there's a Z here because this depends on the charge, the amount of test charge, okay, delta rho, remember. But for V effective, this is purely the Coulomb interaction between 2 electrons in solids. However, the modification or this kind of correction to the bare unperturbed Coulomb interaction is exactly the same as U effective. Namely, the U modify the V, and the V modify the U. So this is what I call this mutual inference, and the way that they inference one another or each other is precisely through this RPA type of a ring diagrams, exactly the same way. Except now, if you evaluate this V effective, you simply just interchange U and V. So that's all. Okay, because U and V are nothing but the Coulomb potential. So just from different charge source, and they mutually inference through exactly the same RPA manner. And without the help of classical Poisson equation, we are able to derive the screening of a Coulomb interaction. And the way that we treat this is precisely by considering this kind of a charge density operator rho as our most important operator, rather than in the Hartree-Fock approach that we don't consider this density as the basic operator in our formalism. Okay, so the lessons to be learned here is that we need to really use the correct language and the operator to express our Hamiltonian, and then the physics becomes clear and all the results are reasonable. So that's all about this screening of a Coulomb potential. So you may wonder, this kind of a simple result can be derived without the help of RPA. For example, if we could derive this Thomas Fermi screening wavelength, why bother using more complicated RPA? So my answer to this question is that yes. So as I mentioned, this result, the Thomas Fermi result, is actually the zero temperature limit and small moment transfer limit of a more general generic dielectric constant or function, epsilon q and t. Right? So yes, we can reproduce this Thomas Fermi in this limit, zero temperature, q equals 0 limit, right? And of course, we could use semi-classical way or Thomas Fermi approximation to get the Thomas Fermi results, of course. However, the semi-classical results, can only study this limit. In general, when this Q is not that small and temperature is actually finite, of course, there is no way that you could use semi-classical Thomas Fermi approximation to get a more general result for a dielectric function, which is a function of moment transfer Q and also the function of temperature. So if you look at this chi of 0, you'll see my statement more clearly because, in the limit of Q goes 0, we could do the Terry expansion. But what about in general Q, where Q is not 0 or it's not small? So when Q is not small, we need to numerically evaluate this ratio, right? This difference in Fermi function, the difference in the free electron connecting energy. So, which of course cannot be obtained or derived by Thomas Fermi or semi-classical result. And therefore, we should rely on this RPA to get the more general situation where the moment transfer is not small and temperature is finite. And that justifies, the approach that we use here is actually the only way that we get the more general behaviors of a electronic, say, dielectric constant in metals, and no other way. So the semi-classical approach can only, address a specific tiny window or limit of this more general dielectric function. But for the rest of this, phase space, there's no way. And I suppose that everyone, gets the point that we first need to use the second quantization approach, and secondly, we have to use the proper, say, language or operator, namely, in this case, the electron density operator for the Hamiltonian, and we can do RPA and to get the screening of a Coulomb interactions. And we can also get this most general dielectric constant of solids in ordinary metals at any moment of transfer and any temperature. But in general, this dielectric constant function is not just a function of Q and T, but also external frequency or omega. It is a much more complicated function, temperature, moment of transfer, and external frequency or omega. So you can shine the laser beam to the your metals and study this dielectric constant response, and in the scattering event, so that you get external energy or frequency and this momentum transfer between the incoming and outgoing, say, photon or electron beams, and at any given temperature. So this dielectric function is, in most general form, a complicated function of omega, q, and t. So we just study these two parameters, q and t, dependence of that dielectric function. But in general, we could study this omega dependence. So, and this omega is actually tightly linked to the plasma oscillation frequency, right? So it's called a dynamical dielectric function. So this will become, the topic of another solid state class. All right. So let's take a short break. When we come back, we'll go to another topic. So we finished this, Coulomb interacting electron gas, today, and we will go to another chapter, which is studying bosonic system, such as phonons, electron-phonon coupling. But before we study electron-phonon, we should study the Bose-Einstein condensation phenomena that everyone should know. Okay, so let's take a short break. So let's start a new chapter, which is about to study bosonic systems. And before we study bosons in solids, let's just review the basic phenomena of the bosons, free bosons, namely the Bose-Einstein condensation phenomena, or BEC. So this phenomena, or this physics, was predicted in early 20th centuries, like 1920s, by Bose and Einstein. That's how we call this phenomena, Bose-Einstein condensation. And they predicted that for bosons without interactions, just free bosons, at ground states, they like to occupy in the same ground state. And so that all bosons like to get together because there is no Pauli principle, and the Pauli principle applies only to the fermions, not the bosons. Okay, so there is no restrictions on this number of bosons that they can occupy in the ground state, and as a result, they show that all bosons will occupy in the same ground state. As a result, you get a macroscopic matter wave, in the sense of a diploid matter wave, so that you get a huge matter wave here, which consists of overlapping, each individual boson wave functions. Okay, so you can imagine that all these little bosonic wave functions get overlapped in the ground state, so altogether they become a huge matter wave with a very large diploid matter wave, lambda dB. And this is the prediction made by Bose-Einstein in the 1920s. But later, it's very, very later, like how many years are apart between these two time, which is over about 70 years later. So in 1995, experimentalists in MIT and in Colorado, so they used a laser cooling technique to really cool down, temperature to the lowest temperature they can reach, to almost zero temperature, and they really found such nice accumulations of the bosons in the ground state. So they really see this huge spike of the matter wave macroscopically. And so this is really a triumph of this solid state physics, because we knew from the early 20th centuries that this is going to happen. But due to the technology and experimental techniques, people couldn't see that until we have some revolution about the technique and other new inventions of this experimental approach to reach the really cool temperature, we are able to really see this phenomena in experiments. Okay. Again, so this is many body phenomena for bosons, as we have defined this boson creation and destruction operator. So we will later derive such a BEC phenomena, but let's just use this result to actually define such a many body boson wave functions. Suppose the ground state phi 0 of a n boson are in the ground state, which we denote this ground state by phi 0, and we destroy the boson in this many boson wave function. So we get square root of n, the prefactors we already derived that some time ago, times this many body wave function of bosons with total number n minus 1, because we already destroyed the boson. So likewise, if we like to increase the boson number by 1, on top of this n boson ground state, we applied a dagger on that ground state wave function. We get the prefactor square root of 1 plus n times this phi 0 of n plus 1. And this boson creation and destruction operator satisfies this commutation relations. Commutator between n and a dagger is actually 1. And such a free boson Hamiltonian is expressed in terms of such a simple Hamiltonian, whereas epsilon k represents the kinetic energy of a free boson, and a dagger k is the occupation number operator to count the boson number in the momentum states. Okay, and each boson carry the amount of h bar squared k squared divided by 2n kinetic energy. So such a free boson Hamiltonian, of course, we need to add a chemical potential term mu to that free boson Hamiltonian. So later we will show by computing the average value, excitation value of this occupation number operator a dagger a in k space, and we can show that in the zero temperature limit, we don't need to put extra energy to add or remove a boson, meaning this chemical potential mu, below a certain temperature, which we call this TBEC, is a crossover temperature to get Bose condensation. And when temperature below this TBEC, it doesn't take any effort to add one boson to the system, so that you get huge accumulations of boson occupations for temperature low enough, and that's how you get this BEC. And these physics is already hidden in this Bose-Einstein distribution function, which is the sum over k of this occupation number expression value of such a boson number. And we know that Bose-Einstein derives such a Bose-Einstein distribution function for a boson, for free bosons, and this is the MB, which corresponds to the boson occupation at any given temperature, and the energy and chemical potential. So remember, this could be derived in your statistical mechanics, right, at the undergraduate level. And we know that for fermions, this is a plus sign for fermions and minus sign for bosons. So this plus minus sign plays a crucial role here, because for the plus sign, you get Fermi-Dirac distribution, where below the Fermi energy you get full occupation, and above the Fermi energy you get empty state. Okay? Because of this minus sign for boson systems, things dramatically changed, because you will see later that there is a divergence of this Bose-Einstein distribution function, the zero temperature limit, and when chemical potential almost vanishes there. And as I mentioned, this minus sign is already a hint to the BEC phenomena. As you can see very clearly that if mu is 0 and epsilon k is 0 and temperature is low enough, which is finite but low enough, then this denominator already vanishes, because e to the beta, which is finite but small value, and epsilon 0 and mu 0, minus 1. So this is e to the beta times 0 minus 1. Okay? So you already see this phenomena emerges in this limit when temperature is low enough and mu is 0, epsilon almost 0, so you got e to the power of 0 minus 1, which is what? 1 over 0, which is infinity. And so without much of this calculation, so by looking at this Bose-Einstein distribution function, you will immediately see something strange must happen, because there's a minus sign here. So when this exponent of this exponential function is 0, then e to the power of 0 is actually 1, and 1 minus 1 is actually 0. So you must encounter such a divergence at some point. And that's the difference between this fermionic and bosonic statistics, because of this minus sign here. So now let's just more rigorously derive such a divergence. We could define this number density per unit volume, little n, as the total number of bosons divided by your volume, and you could use this Bose-Einstein distribution function and re-express this in terms of the energy integration, multiply, and you insert this density of states rho of epsilon in this energy integration. And the energy ranges from 0 to infinity, and so you could define a more convenient parameters, which we call z and x, where z is defined as e to the beta mu, and x is defined as beta times epsilon. So in that sort of a dimensionless variables, this number density per unit volume of the bosons is expressed in terms of this dimensionless integration multiplied by some prefactor. So we will focus on the evaluation of this integral, which carry this kind of a square root x dependence, because this is a three-dimensional system. If you evaluate the density states for free bosons, you get square root of epsilon, that's your density of states, and you change variables and you get to this integral. So you could Taylor expand this kind of complicated functions encircled by red, and imagine that z is actually smaller than or equal to 1. But for arbitrary x positive, you could always Taylor expand this ratio, and which leads to such a summation over p, and p runs from 1 to infinity. Okay, so p is integer, and inside the summation you get z to the power of p times e to the minus p times x. So this function is actually convergent if z is actually less or equal to 1, and it diverges if z is larger than 1. So in particular, we need to sum over this kind of factor, which is e to the minus px times square root of x dx. Okay, so you plug in this summation back to the integral over here, and you arrive such a integration. Right? And you could actually use this gamma function to actually simplify this integral, because you could really change the variables from x to y. If you define y, it's actually p times x. So using this new variable y, you can re-express this integral in terms of 1 over p to the power of 3/2 times this integration over y, and this integration is nothing but gamma function, which is defined as this integral over the y, and inside the integrand you get y to the power of t minus 1 times this e to the minus y. So this integral that we need to evaluate is nothing but gamma with a t equals to 3/2, which is given by a constant, square root of pi divided by 2. So now you could just plug in this gamma function back to this Bose-Einstein distribution function in terms of this dimensionless quantity z, and little n is given by this temperature dependence to the power of 3/2 multiply this g 3/2 function. This g 3/2 function is a function of z, which is a function of, it's a summation over p, and inside the summation is z to the power of p divided by p to the 3/2. Okay, so this so far is just a change of variables. Let's take a short break. When we come back, we will discuss the behavior of the little n, especially the behavior of this g 3/2 function as a function of z. And by analyzing this behavior, g 3/2 function, we'll actually recover this BEC phenomena that we observed without any calculations right here. Okay, so let's take a short break. So before the break, we can re-express this, the number density of the bosons, free bosons at any temperature in terms of this g 3/2 function, this function of z, where z is defined as e to the beta mu. Okay, and this g 3/2 function is actually the summation over this infinite number of terms over p, integer value of p, ranging from 1 to infinity, and the inside this expression summation, it is the z to the power of p divided by p to the power of 3/2. So this function could be evaluated numerically, and the result is given by this plot between z being 0 and 1. So when z is small, where we will just mentioned later, which is the high temperature region, this function is almost linear in z, and then it turns up to this boundary value when z is 1, and this boundary value is 2.6. But the special unique properties of this boundary value is that the first derivative of g function is back to z near this boundary z being 1 is divergent. So the first derivative of this g function is back to z at this boundary z being 1 is infinity. So we will come back to this later. At this boundary where z is actually 1, this G3 halves function is nothing but a special function called Riemann zeta function, which is defined by this summation over 1 over p to the power of s, where p ranges from 1 to infinity. So that's called Riemann zeta function. And this sum over p from 1 to infinity of this 1 over p to the power of 3 halves is nothing but Riemann zeta function of 3 halves of s and this Riemann zeta function s being 3 halves is given by 2.6, and that's how you get this value from. All right, so that's evaluate this derivative, the first derivative of this G3 halves function back to z, which is given by this, and you could check your table of integration or summation. When z goes to 1, this summation diverges. So something diverges here, and we will link this divergence to the BEC phenomena. So we could, in general, just re-express this, say, this relation that we just defined, this number density of bosons as a function of G3 halves and also this prefactor. We can actually re-express this in terms of this form where G3 halves is a function of boson density multiplied by this temperature prefactor. And so by expressing this equation this way, we can determine the chemical potential. Okay, you can see that on the left side of the equation, you get G3 halves as function of temperature and mu. Okay, but on the right-hand side, it does not depend on chemical potential. So the chemical potential is hidden in this G3 halves function, and we can actually solve this equation for this chemical potential if we have fixed the temperature and the boson number density. So let's just look at the behavior of the chemical potential, because that determines how much energy that we need to inject to actually add or remove a boson, right? So we need to know this chemical potential as a function of temperature, because that is a function of temperature. And as I mentioned, in the low enough temperature, below TBEC, it doesn't cause any energy, or the chemical potential is actually 0, but in the higher temperature limits, the chemical potential is non-zero. So let's just derive or estimate how much the amount of the chemical potential is from this equation here. So first, let's look at the high temperature limit. When T is very, very large, then we could actually plug in this G3 halves function of z. Remember, z is actually e to the beta mu, right? So when T is very, very large, which means that beta is actually 1 over kBT, is very, very small. So when beta is really, really small, we can simply Taylor expand this G3 halves function, and if we do so, and we get this linear approximation. Okay, of course there will be higher order terms in the expansion, but when beta goes to 0 limits, this is the leading contributions of G3 halves as function of z, which is just linearly proportional to z. Okay, so we could actually use this approximation in the high temperature region to rewrite the chemical potential and determine this value of mu in terms of minus 3 halves kBT times the log of this ratio. So as you can see here, the chemical potential is negative, right? Which means that when temperature is high enough, this mu actually goes to minus infinity. And while this could be confirmed, this linear dependence of G3 halves, when Z is actually small, is actually, could be verified from the behaviors of the G3 halves, when Z is actually small. So now we actually understand the chemical potential for free bosons, the high temperature limit is actually negative. So you can think about physical interpretation of such a negative chemical potential. What does it mean? Okay, so we will come back to here later. So let's just decrease temperature from the high temperature regime to the low temperature regime, and we could again try to determine the chemical potential in the low temperature regime. And we will show in just a moment that in this low temperature regime or limits, the chemical potential approaches zero, below a certain temperature. Okay, so while this can be done by looking at this, boundary value of Z, where Z is actually 1 in this limit, because we already learned that this BEC phenomenon occurs at very, very low temperature near the ground state, and because bosons can actually occupy to the same ground state, there's no restriction, which means that the chemical potential must vanish there, right? So which means that we should get this result correctly by analyzing this G3 half function. In that limit, Z is actually approaching to 1, okay, because mu is almost 0 and beta is finite. Okay, so e to the beta times 0 is actually 1, and this is precisely the limit that we should consider, which is G3 halves when Z is actually 1, which is 2.612. And you can very clearly see that as you lower temperature, the chemical potential is actually coming from the very negative value, and then it starts to decrease the negative value, and as T goes 0, you immediately see that mu will approach 0, okay, because this is dependent on this T times log T, okay, and that's precisely what we expect. So you could see very clearly that when T hits the critical value at Tc, which we call TBEC, the chemical potential vanishes. Okay, so as you can see clearly from this plot here, that we could determine this chemical potential numerically by solving this equation self-consistently, right? So given the temperature and the density of bosons, and this mu, okay, so this result can be solved numerically, and we could plot this chemical potential as function of temperature at different regimes. The high temperature regime, this is the negative value, and as the temperature is lower and lower until it hits 0 chemical potential limit at a finite temperature Tc. When that happens, mu is strictly speaking 0. And this is called the BEC temperature, the Bose-Einstein condensation temperature, which is given by this relation here. So there will be a macroscopic condensate bosons when temperature goes below TBEC. So in other words, this equation can be satisfied when temperature is below TBEC, and as you change your lower temperature even further, you get more and more percentage of your boson get in the condensate state. All right, so this N0 represents the number density of bosons that's in the condensed or condensate ground state. So number of bosons in the ground state, in the BEC state. So you can see clearly that to satisfy these equations, you even lower temperature below TBEC, this N0 should be increased in order to satisfy this equation, right? So which means that N0 as function of temperature, as temperature is lower, should actually increase. Okay, and until everybody, all the bosons are condensed in the same ground state, okay, in the zero temperature limit. Let's take a short break. When we come back, we will again further analyze relation between the chemical potential, temperature, and the number of bosons that stay in the ground state, in the condensate. Okay? Yeah, let's take a short break. So let's finish this. As I mentioned, you could solve this chemical potential as function of temperature by solving for the relation between this boson number, occupation number, through this Bose-Einstein distribution function. And as we already derived, that when temperature is high enough, this chemical potential is negative. When T reaches TBEC or below, the chemical potential vanishes. So, which means that when temperatures are below TBEC, all particles tend to be in the ground state because the chemical potential vanishes. So I emphasize the tend to be, which means that not all the particles are in the ground state at any temperature below Tc, but a sizable percentage of the bosons are in the ground state. The remaining percentage of bosons are still in excited state, okay? Which means that out of n particles, a macroscopic number N0 occupy the ground state, which means that the macroscopic number means that N0 is actually the same order of magnitude as the volume, which tends to be infinity. Okay, so which means that not 100% of bosons are in the ground state when temperature is just below the Tc, but a sizable, a macroscopic number N0, which approaches infinity, but still not 100%. Okay, it's sizable, but not 100%. Okay, so that's what it means. All particles tend to be in the ground state. Okay, but of course, when temperature really hits zero, all particles will occupy the ground state. That's for sure. But between zero temperature and TBEC, a sizable percentage of bosons occupy the ground state. Not all of them. Okay, and so you can see this relation that I stated over there more rigorously by looking at this, a number of bosons which occupy the ground state, and 0, which is given by 1 over e to the minus beta mu minus 1, right? Because epsilon k, the kinetic energy vanishes. Because at ground state, for free bosons, the energy is actually 0. Therefore, this mu is given by this minus kBt times log of 1 plus 1 over n0, and you immediately see that, this is satisfied if, n0 approach infinity. So that mu in that limit should vanish, okay? Right, so mu vanishes only if n0 is very, very large, okay? But we know that not all of them stay in the ground state, so let's just, separate these two different contributions to the boson number the first part is the condensate part, where this boson stay condensate in the ground state, and the second term is the terms that the boson state, the remaining boson stay in the excited state, where K is non-zero. And you add these two together, you get the total number of bosons, which means that a sizable percentage of bosons, when T is less than TBC, will occupy the ground state, but the remaining particles are still staying in the excited state, right? Okay. So then we could simply just use this result to re-express this number density in terms of the condensate part plus the normal bosons, where this bosons stay in the excited state. We call this N normal, and this N normal can actually be estimated by using the same trick that we did before. Remember, this is given by, this integral is given by the gamma function of 3/2 multiplied by Riemann zeta function of 3/2, right? Okay, and this altogether will lead to such a temperature-dependent prefactor. Okay, so the temperature is actually to the power of 3/2, and we will actually use that relation. Okay, so you could simply just re-express this relation of this total number density and in terms of the condensate part plus the non-condensate part. Okay, and you could rewrite this prefactor in terms of Tc or TBC, and this is the simplified version of this equation, which tells us temperature dependence of the condensate part of bosons as a function of temperature, which is 1 minus T over Tc to the power of 3/2. So this is the behavior that is close to Tc. Okay, so you can see that when temperature is 0, all the bosons stay in this condensate ground state, where this N0 is nothing but N. Therefore, the ratio is actually 1. Okay, N is actually the N0 when temperature is precisely 0. But as you turn around the temperature a little bit, but still below Tc, the percentage of your condensate part of the boson is decreased until it hits 0 when temperature is exactly TBEC. And above TBEC, no bosons stay in the ground state, and all bosons stay in excited state. So that's what we can summarize here, that for T less than TBEC, a part of particles, which is macroscopically sizable percentage of particles, stay in the ground state, which means that N0 is somewhere between 0 and M. But when temperature is above TBEC, all particles are in the excited state, where no particles stay in the ground state. And this kind of a separation between the normal or excited state bosons from the condensate bosons could help us to rewrite this number operator in terms of the both condensed part N0 and the excited state part, okay, which is sum over all this boson number, occupation number, A dagger K prime, A K prime, where K prime is non-zero. Okay, but the condensate part could also be re-expressed in terms of the boson number operator A0 dagger A0, where A0 refers to the destruction operator of a boson in the condensate part. Okay, but we know that this is nothing but a number. Okay, so when this boson gets condensed, the operator A0 dagger or A dagger is nothing but an average value, or classical value, simply just square root of N0. So both A dagger 0 and A0 become classical values when the bosons are condensed in that state. Therefore, the operator reduces to the number, which is square root of n0 when the bosons are condensed. But the remaining parts of bosons, which are still in excited state, this A and A Dagger operators are still quantum mechanical operators, but especially when these bosons are in the condensate part, the operators reduces to the classical value, square root of n0. So that's how you get the expression that we just wrote, where A0 acting on phi 0 of n is actually square root of n0, phi 0, and minus 1, and so on. Okay, so let's summarize the BEC phenomena. And there are many examples of this bosons, bosonic atoms in the periodic table that have been shown to have such a BEC phenomena experimentally. And in particular, say, rubidium, lithium, and other bosonic atoms in the periodic tables already have been shown to have such features of BEC. Okay, so you could look at these corresponding chapters in our textbook or in reference that you found in the internet. There are many review papers that you can find for this BEC phenomena. Okay, so that's about it. And next time, we will use this bosonic operators to derive this phonon, in solids, which is harmonic oscillators of atoms, and we second quantize this harmonic oscillator energies, and we derived this phonon mode. Okay, and that will lead to electron-phonon couplings at a later time, and which gives rise to attraction between two electrons in metals to form the BCS superconducting state. Okay, but of course, for interacting bosons with no fermions in there, we have a very interesting phenomena called superfluid phenomena. But we may not have enough time to talk about the superfluid behaviors. But at the end of the semester, I may just give you a sketch of this superfluid phenomena, which is on top of this BEC, we add interactions among those bosons, and low enough temperatures, those bosons can actually form the superfluid where there's no dissipation, no energy lost when they move around. And this is the charge-neutral version of the superconductor. But in any case, let's see how much time we have left in the remaining part of the course. Okay, so I'll see you next time.